And so we have two examples, one of each type. So we're going to have two examples showing you one of each type between the two different types of distributions that we can test, the two different nulls and alternatives that we saw. In this one, we want to see if the distribution of US residents is different today than it was in 2000. Back then, 20% lived in this region, 20% lived in that region, 30% in this region, 30% in that region. Now we select 1,000 households, and we want to see do we follow the same distribution or not? Notice again, this is work problem without the use of a calculator. This is one that the math should work out pretty simple for you. And so how do we know which type of test this is? If this is a goodness of fit test where we're saying all of the categories are equally likely versus a goodness of fit test where we say it follows a proposed distribution. And again, it just goes back to what do I think is happening? Do I think all of the probabilities are the same or not? Notice here I'm comparing to a distribution where in some of the regions of the country we're at 20% and some are at 30%. Notice those are not equally likely. If this said 25, 25, 25, 25, I could say this is that first case where I would say that my null is all of the p's are equal. And then my alternative is at least one of the p's is different. But in this case, these are not equally likely because I think that the distribution follows something slightly different with more people living here than here. Okay, and so that's how I know that my null is going to be the distribution is the same. Now the same as what? And this is where we want to make sure we're just careful with our hypotheses, that we're using the context of the problem. I'm saying the distribution is the same as it was in 2000. That's where those numbers came from, right? Or I could have put the distribution is the same as I think it is, right? It's just some sort of context to what we're dealing with versus the alternative, the distribution is different from the year 2000. Our conditions, our sampling methodology looks fine. Now we need to work through all of our expected counts. The expected counts are going to be needed for the problem and they're needed for the test statistic and for the assumptions. Okay, so we're needing them for both. Again, the expectations, I take the sample size. The sample size is 1,000. Multiply that by the probability in each group. So 20%, so 1,000 times 20%, 1,000 times 20%, 1,000 times 30%, 1,000 times 30%, which means I'm expecting, and you may want to make an extra little note, back up here, you may want to make a note, what's my expected count? So expected and say, okay, this is Northeast is 20%, so that's 1,000 times 0.2, so 200. Midwest was 20%, so that'd be 200. South was 30% of 1,000, be 300. West, 30% of 1,000, be 300. So you could put the expected counts right below this as well because you're going to need them when working the problem. Our smallest expected count is 200. That is much bigger than 5. So our assumptions are good to go. And so we have 4 groups, which gives us 3 degrees of freedom. So our chi-square test statistic, we'll notate, as usual, with the degrees of freedom, subscript 3. And then we just plug and chug. We wrote down all those expected counts below the observed counts to make it easier for us to fill in this formula. We're going to take those 4 observed counts. We're going to subtract it by each one's respective expected count, even though 2 of them duplicate. Like so. And then the math should work out pretty simple for you. 210 minus 200 is 10. 10 squared is 100. 100 divided by 200 is 1/2. Same answer here because that's negative 10 in the numerator before you square it. Negative 10 squared, also 100. Make sure you note that when you square 10, you get 100. When you square negative 10, you get 100. Just be careful if you're typing it into a calculator. The best part about technology is it does what you tell it to, and the worst part about technology is it does what you tell it to. Some of those calculators, if you type negative 10 squared, you don't put the negative 10 in parentheses. Or you don't, and you're not careful there, it'll think you mean 10 squared and then make it a negative, right? But we both know that negative 10 times negative 10 is positive 100. So just be careful there when you're calculating this, that this would become negative 10 inside the parentheses squared makes positive 100 divided by 200 is 1/2. So 1/2 plus 1/2 plus, this would be negative 30 squared. This would be positive 30 squared. 30 squared is 900. 900 divided by 300 in both cases is 3. So it's 1/2 plus 1/2 plus 3 plus 3, which is 7. We have a right tail test. You can draw the same curve for the chi-squared as you would the f. It looks roughly the same. It doesn't have to be perfect. The key is that you make sure you put the right critical value there, given our alpha. In this case, our alpha is a 0.05. You'll notice your chi-square table does have different alphas, just like your t-table did. Remember, the F couldn't do that because we had to use one of those rows for numerator degrees of freedom and one for denominator degrees of freedom. Back in the world of only one type of degrees of freedom, we could have different alphas. So notice again, that's a slight change there. Our critical value here, we could look up in our table, would be 7.81. So our test statistic, not quite inside that rejection region. And when we find that p-value, again, I turn to Excel for that. The table isn't going to help me, again, be able to write out the probability statement. This one, just like the F, is very simple. It's put the statistic here in the symbol form. It's always greater than or equal to for the F and the chi-square because those are right-tailed distributions, and then put the test statistic in. So be able to write that p-value statement out, and then Excel gets you your answer of 0.072, which is larger than 0.05. So again, here now it's just lather, rinse, repeat. Because our test statistic does not fall in the rejection region and our p-value is larger than our alpha, we fail to reject the null. And that means we cannot conclude the alternative. The alternative is that the distribution is different from 2000. So I'm just going to write that out in a little bit nicer of words and say that we cannot conclude that the distribution of residents across the country is different than it was in 2000. And so that's one example. For the second example, we want to know whether or not the proportions of children born on each day of the week are the same. Notice this right here lends me to this idea that we have this equally likely scenario, right? Because it goes back to what am I proposing? What do I think? What do I hypothesize? Lots of ways to word that. But it's this idea that I'm saying, yeah, all the days of the week probably are the same. That's what I'm wondering. So that leads me to the type of test where my hypotheses are all of the probabilities are equal versus at least one p is different. So make sure you understand the difference between these two types of setup. The first setup was, I think the distribution follows this, and it's whatever this is, doesn't really matter. It's just that this isn't an equally likely scenario where they're all the same. This is a little bit higher than this one. This is a little bit lower. This one, this is what I'm proposing. But in this latter scenario, I think all the days of the week are the same. Notice when we wrote it out in generic way, we put P1 equals P2 equals all the way to PK for how many groups there are. This time I don't have to put K. I want to put 7 because I know there are 7 groups. So I always want to specify how many groups you have. If I had fewer groups, I would not use the dot dot. I would actually write them out, but that seemed a little bit of annoying. But you could have written P1 equals P2 equals P3 equals P4 equals P5 equals P6 equals P7 if you really wanted to, and that would have also been acceptable. Again, our sampling seems fine. Our expected counts, the good news on the equally likely front is that our expected counts are always the same for every group, because if again, we always assume the null hypothesis is true in these hypothesis tests. So if the null is true and all of the probabilities are the same, all of the probabilities are 1/7. Make sure you catch that because you're going to have to find the expected counts. Well, how did I get that 1/7? Well, if all of the probabilities are the same and everything's equally likely, it's just 1 over k, right? If I have 4 categories and everything's equally likely, my probability is 1 out of 4. If I have 6 categories, like rolling a 6-sided die, and I think that it's equally likely it's a fair die, then roll landing on each one is 1 out of 6, right? So in this case, I have 7 days of the week. I think they're all equally likely, so my probability for each category is 1 out of 7. 1 out of 7 times 500 means my expected count for each group is 71.4. If k is 7, that means we have 6 degrees of freedom. And then from there, it's just plug and chug. You will need a calculator. Notice we write out all of our observed counts. Here, we subtract the expected counts, square them, and then divide by that expected count. Again, in this case, like we said, our expected counts are all the same. That's nice. In the proposed distribution world, they may have some repeats, but they may all be different, right? In a world where I go back to that previous problem where we had the regions of the country, I could have easily said that the distribution was, 28% in this region and 22% in this region and 26% in this one and 24% in this one. Well, they're all going to be different in that case. Okay, so they could be anything there, but if we have this, all the probabilities are the same, those expected counts will be the same. That makes your life a little bit easier, but it's still going to be a little bit hairy on the math there. And we would get 6.18. And then again, it's pretty simple to take it on home from here. Find our critical value from the table would be 10.64. Notice we are using a 0.1 level of significance, so make sure you are looking for that, just not blindly assuming 0.05 on every problem. Our p-value, again, be able to write the probability statement, and Excel will bring you home with the actual probability. And just like the last problem, in this case, we are going to fail to reject the null, which means there is not sufficient evidence to say that at least one of the days is different.